computer graphics and visualization subject in that module 4. Yesterday we have discussed, from this module we have discussed visual surface detection. Now we are going to discuss 3D viewing concepts, right? As I told, outcome of this is apply the concepts of viewing and visual surface detection of 3D objects. Means after studying this subject, as I told, you can able to apply the concepts of viewing and visual surface detection of 3D objects, right? Then next, overview of three-dimensional viewing concepts. Means what is the difference between three-dimensional viewing and two-dimensional viewing? There is a slight difference between three-dimensional viewing, means three-dimensional objects, and two-dimensional objects. That's why overview of three-dimensional viewing concept. When you model a three-dimensional scene, when you are going to model any three-dimensional scene, each object in the scene is typically defined with a set of surfaces that form a closed boundary around the object interior. Means for every object you have to define set of surfaces that form a closed boundary around object interior. Means for object interior you have to consider all the other surfaces which are seen in our eye, right? That is 3D object modeling, right? Viewing functions process the object descriptions through a set of procedures that ultimately project a specified view of the object onto the surface of a display device. Means then viewing procedures, whatever viewing functions are there, they will process the whatever description you have described in a scene, all the surfaces, all the color, whatever you have mentioned, everything will be processed, ultimately project a specified view of the object on the surface of display device. Viewing three-dimensional scene, right? Again here, whenever we are drawing three-dimensional object, in two-dimensional only we have considered two dimensions, that is x and y. Object was also, whatever object we have considered, that also in x and y, then whatever we are going to display, that was display device also two-dimensional. But in three-dimensional, the complexity will be added because of additional dimensions. Additional dimension in the sense, in three-dimensional, object is in 3D space. Object is in 3D space. That 3D object we have to capture in our camera, then that has to be displayed on monitor, which is a 2D device, right? Means we have to convert 3D object into 2D object, then we have to display it in monitor, because all the monitors, all the display devices comes in a 2D space. That's why this is additional complexity is there in three-dimensional objects, right? Because we have to convert 3D to 2D. Then during this process we have to do some calculations and some processing for conversion. Then at the end we are going to display it on the monitor, which is a 2 dimension. That is the complexity. Additional dimension adds some complexity in 3-dimensional rendering, right? Then viewing three-dimensional scene, viewing a three-dimensional scene. How to view three-dimensional scene in general? To obtain a display of three-dimensional world, coordinate scene, we first set up a coordinate reference for the viewing or a camera parameter. Means like in synthetic camera, means how in real life camera how we are taking a picture, like that here also we have to consider, that is a, means we have to fix coordinate reference for viewing or a camera parameters. Means here also we have to set the camera parameters, as I told, because we don't have camera in OpenGL, we have to assume that there is a camera, then we have to set that camera parameters. How we'll set the camera in real world? Means we will set a camera, then from that camera we will take a picture in real world. Like that in OpenGL also we have to set camera parameters, right? That is a coordinate reference for viewing or camera parameters, right? This coordinate reference defines the position and orientation of view plane. This coordinate reference defines the position and orientation of the view plane or projection plane that corresponds to camera film plane. Means in real life camera, normally first what we will do, we will set a camera. Means we will fix a camera somewhere, then from that camera we will take a picture, right? That is what this coordinate reference defines. Whatever camera we are setting in this OpenGL software, that position is orientation of view plane. Means in that, in camera, in a film you are taking a picture. In real life camera, once you capture a picture, that comes and falls on a film which is available in your camera. Like that here also we have to set that. Means your coordinate reference of viewing, for viewing means that is a view plane we are setting, that is a projection, that is also called a projection plane, that corresponds to camera film plane. Means if you compare this view plane with your camera, there is a film plane. Means there is a film in your camera, that is nothing but view plane in this. In figure if you can see, means you have to first set a view plane, means camera. If you set a camera, then you can observe any of the object. The cone is observing seen in that camera. Then whatever the view plane is nothing but your film plane that is available. That is a view plane we have to set. That is what reference frame we have to set here, right? Then projections. Then next we have to do the projections. Means this is overview of how the picture will be taken in OpenGL, right? Then afterwards, first you have to set the camera, right? Here also in real life also, first we will set the camera. Then after setting the camera, we will take a picture on the film. Here also that setting a camera is nothing but we are taking a picture on the film. That is a projection plane, that is called, right? Then afterwards projections. Then afterwards you start projecting. Unlike a camera picture, we can choose the different methods for projecting a scene onto the view plane. Unlike means how you have projected that picture on the camera film, like that here also you can project that whatever picture you have taken in your camera, that you print it on a plane. There are printing it on a view plane, or there are two different methods, one in parallel projection, one is perspective projection. But in real camera, this parallel projection is not there. Always the real camera takes a perspective projection, but that additional feature will be there in OpenGL. Means whatever picture you are taking, you want to take that printout of that picture on a film, that is called a projection plane. Then that has to project, means nothing but capturing, nothing but we have to project that object. Whatever object we are capturing, the image of that object has to projected in a projection plane. For projecting, there are two methods. One is parallel projection, one is perspective projection. Parallel projection will be mostly used in architectures. Parallel projection will be used in means building designs and CAD CAMs. Means whenever we want a front view, top view, side view of the object, any object, that time we are using the parallel projection. Means whenever you are seeing any object, we will draw the parallel lines from that object. Then we will take the printout. You can see the left side image in this slide. My left side image in this slide. That is means whenever you want to see any object, you can stand in front of that object. Then exactly whatever in front picture is there, that will be viewed. That is a front view. You can go side view. You take the side view. Whatever only side view exactly means parallelly whatever parallel image is there, that will be seen on parallel side view. Then top view like this means parallel, means rays are traced parallelly, then those will be used parallel projection. As I told, means architects, building architects, then CAD CAM design, they will use parallel projections, right? Next is perspective projection. Normally real life camera does this one, perspective projection. Then our eye also does this one. Perspective projection in the sense the camera will be somewhere, then you are projecting that camera on some object. Then as and when your camera and object starts moving away from the, means object starts moving away from the camera, that time the object looks smaller. When object comes near to your camera, object looks bigger. Again, one more example for perspective projection is once you stand train track, which is straight line, which is a straight train track. If you stand at one end of the train track, then if you see for longer distance, then you will feel that the tracks are coinciding at some point. That is what perspective projection. Normally our eye looks in a perspective projection, then real life camera also does perspective projection. That means depending on what type of picture you want to take. If you take a perspective projection, that you will feel a realistic pictures, right? Advantage of perspective projection in realistic images can be captured by using perspective projection. Parallel projection, where some people will use, that is means for for drawing building architectures, for CAD CAM design, they will use a parallel projection. But for realistic images, we will go for perspective projection. Means you project those objects, whichever object you are capturing through your camera, those has to projected on your projection plane as a perspective projection. This is then projections. Then afterwards you have to do depth queuing, right? Afterwards you have to do the depth queuing. Means these are the procedures you have to follow whenever you are taking a picture, whenever you are projecting, whenever you are viewing in 3D viewing, right? Then next is the depth queuing. With a few exceptions, depth information is important in the 3-dimensional scene. Means in 2-dimensional scene, this was not there. This was not there because there was no depth, right? In this case, when you are using a 3-dimensional scale, you have to feel that whatever object you have drawn in 2-dimensional, actually that object was 3-dimensional, but you are going to draw it on 2-dimensional, but that has to be felt like a 3-dimensional object you have drawn on the monitor. For that is the reason we have to feel the depth queuing. With few exceptions, depth information is important in 3-dimensional scene, so that we can easily identify for a particular viewing direction which is the front and which is the back of each display object. Means Depth information allows us to identify which is the back face, which is the front face of that object. If you don't include depth information, then you will feel that only that object is in only, it has only one face, right? That we are seeing in 2 dimensions. That time you will not feel how much, whether that object is having other face or not. For that reason, we have to use the depth information in 3D objects, right? There are several ways in which we can include depth information in the 2-dimensional representation of solid objects, right? There are several ways in which we can include depth information in 2-dimensional representation. Ultimately, we are going to represent in 2D monitor, right? Ultimately, whatever object we have captured through our camera, that has to printed on film, which is a film is a 2-dimension. Only it has X and Y. Any film don't have Z information. That's why. But somehow by adding there are ways to add that depth information in 2-dimensional representation solid objects, right? That can be done in this, right? That is called depth queuing. A simple method for indicating depth with wire means you can display that objects, wireframe models or solid objects. There are again for displaying object. If you want, you can display those objects by using wireframe model, or you can display as a realistic object, right? That depends on which type of object you want to draw. Suppose if you are using wireframe model for displaying your object, the simple method for indicating depth with wireframe displays is to vary the brightness of line segments according to their distance from the viewing position. Means wireframe, when you are drawing object with a wireframe model, you can vary the brightness of line segments, because you are drawing those objects by using a lines, right? When you are drawing using by lines, then you can vary the brightness of line segments to their distance according to their distance from the viewing position. Means if that object is, means you are drawing a line which line is near to your eye, then that lines has to be drawn with a brighter color. Then which line is away from your eye, then those lines will be drawn with a less brighter color. Like that you can vary the intensity of lights of those lines. Then you will feel that yes, that part is, means that is a away face, this is near face. With one image there, you will come to know if I display that object, right? Like that you can include the depth information. Another application of depth queuing is modeling the effect of the atmosphere on the perceived intensity of object. Means if you want to model the realistic object, there is atmosphere also matters on the images, right? If you want to model real life objects, then that depth queuing also you have to include. That's why we have shown 2 images here. One is wireframe model. If you draw that is a teapot you have drawn with a wireframe model, right? Means wireframe models means we have drawn that object by lines, by using a lines, right? By using wire like lines, right? Then the lines near to our eye, we have added more brightness. Then lines which are far away from, means little bit away from our eye, we will add less intensity, so that automatically you will feel that it has 3D object. Similarly, right side, if you are adding the depth queuing in modeling effects to atmosphere, that time again you have to add those one. Means automatically the far away objects will be drawn with a lesser intensity, then near objects will be drawn with high intensity. Automatically you will feel that this is a perspective object, right? Then after that, then identifying visible lines and surfaces. Afterwards, then we have to identify visible lines and surfaces, so that I can draw only those lines which are not visible. We should not draw those lines. We can also classify depth relationship in wireframe display using techniques other than depth queuing, right? Again, there are methods to identify the depth relation without using depth queuing, right? One approach is simply to highlight the visible lines or to display them in a different color. One more way is to highlight the visible lines or display with a different color, right? Another technique commonly used for engineering drawing is to display the non-visible lines as a dashed lines. Normally, whenever you are drawing using a pen and paper, for example, when you are drawing a cube, at that time you will draw 2 rectangles or 2 squares, one front, one back side. Then to join those backside square and front square, then normally you will draw dotted lines, right? Like that is also one way of including depth queuing, right? Without using the depth queuing technique, you can include depth information by drawing like this. Normally you will do whenever we are drawing on paper, right? If you want to draw a cube, first you will draw one square, then afterwards you will draw one more square backside and front. Then to join those to make it cube, then what we will do, normally those edges, means those corners, those 2 corners you will draw with a dotted line, right? That is also one way of drawing cube, right? Or we could remove the non-visible lines from the display, or you can remove the non-visible lines from the display line. But if you remove the non-visible lines from the display line, it is very difficult to identify whether it has other face or not. Means you will lose some information. That's why you will not do that one. Means normally will not remove the non-visible lines from the display, right? If you want, you can remove, but if you remove, then it is very difficult for us to whether it has other face or not. That's why we will not remove in OpenGL, right? You can see this one. But removing the hidden lines also removes information about the shape of the back surface, right? As I told, if you remove the hidden lines, also removes the information about the shape of the back surface of an object, right? And wireframe representations are generally used to get an indication of an object's overall appearance from the back, right? Here you have seen, right? There is one diamond you have seen in A from some angle, right? It is, if you are seeing like this is 3D object, but if you see B, again you are seeing 3D object, but it is very difficult for you to identify what is there in other side in B, right? That's why in C, if you take a C, here in C, what you have done, the hidden lines you have removed, right? Those are the methods you can do for drawing depth information, right? When a realistic view of a scene is to be produced, back parts of the objects are completely eliminated so that only the visible surfaces are displayed. When the realistic view of the scene is to be produced, back parts of the objects are completely eliminated so that only the visible surface are means in last class we are discussing that when the other part is not visible to our eye, then why you want to draw that part in our picture, right? That's why we will eliminate such parts, right? That is, only will draw only visible surfaces of that part that is displayed, right? Then afterwards, then we have to do the surface rendering. Surface rendering in the sense, added realism is attained in display by rendering object surfaces using the lighting conditions and the scene and assigned surface character. Means we have to, again, realism has to be added. For if you want real object to be displayed on your monitor, then you have to take care of what light it has, in which light it is emitting, right? What the property of that object, right? In lighting and shading we have discussed, whenever any object is visible to our eye, definitely there is some light has fallen, then that object has some its property, right? Material has different property, glass has different property, means light observation properties, right? Glass will not, means glass is a transparent. If you take a wood, then that is a different. That's why the surface properties, surface characteristics we have to consider, right? We set the lighting conditions by specifying the color and location of the light source. As we were told, we can set the lighting conditions, specify the color of the light, location of the light source, and we can also get background illumination effects, right? We can also get background illumination, like that is ambient light and all those things we have discussed in the third module, right? Then surface properties of the object include whether the surface is transparent or opaque and whether the surface is smooth or rough, right? Means whenever you want to set a light, means if you want lighting effects on that object, then you can set the lights in OpenGL in any computer graphics software. You can set the light color, you can set the light location, everything can be set so that it can illuminate that light with some color, right? Then surface properties also can be set, because different surface has different property. Wood has different property of light observation, glass has different property of light observation, again mirror has shiny surface, right? These are the different surface, again water, all those things are different properties they have. Those can be set in the surface, in the graphics, so that it can add the realism to our objects, right? Then next is three-dimensional and stereographic viewing, right? Three-dimensional and stereographic viewing. Three-dimensional views can be obtained by reflecting a raster image from a vibrating flexible mirror. Means three-dimensional views can be obtained by reflecting a raster image from a vibrating flexible mirror, right? The vibration of the mirror are synchronized with the display of the scene on the cathode ray tube, right? Then as the mirror vibrates, the focal length varies so that each point on the scene is reflected to a special position corresponding to its depth, right? These are the methods normally we have to follow. That is, first is, means whenever you want to take any image, first is viewing the three-dimensional scene, means in what side or whether you want to view that object from the front side, whether you want to view that object from the right side, whether you want to view that object from the left or top, that you decide, so that image will be fallen on your projection plane. Then afterwards, how to project, how to draw that in your OpenGL, means when you are taking a picture, definitely that picture will be there in a film. That we have to do here by doing a projection, right? There are two methods, parallel and perspective projection. Then depth queuing, then add the depth information so that it can be viewed as a really three-dimensional object, right? Then after that, depth in identity of visible lines and surfaces, then identifying visible lines, you identify visible lines and hidden surfaces. Other than the depth queuing, there are other methods, right? Then that also can be done. Then afterwards, then surface rendering means add the lighting and lighting effects and add the properties of a object, that object surface. Then after that, you can add the realism, then 3-dimensional and stereographic viewing. These are the methods you have to follow whenever you are going 3D viewing, right? Means these are the basic steps we have to do, right? Then the 3-dimensional viewing pipeline. Then for doing this one, we have 3 dimensions, means these are the procedures. These procedures will be carried out in OpenGL by stage wise, right? That's why the 3-dimensional viewing pipeline. First of all, we need to choose a viewing position corresponding to where we would place a camera. What is the first method? Normally in real life, whenever you are taking a picture through a real camera, what you will do? First you will place a camera. Place a camera for particular position. For example, if you want to take picture from the front side, right, you will keep your camera in front side of that object. If you want to take a picture from this side, then you will go and keep it inside, right? That is the first method we have to do. First step we have to do, place a camera on proper position corresponding to where we would place a camera, right? That is position. Then we could also pick a position in the middle of a group of objects or even inside a single object such as a building or molecule. For example, there are means you want to take a picture of some group of peoples, right? At that time, what you will do? You will set one center position among those group. Means one you will target at one position. If you target at particular position, then you will feel that right side how much it is covering, left side how much percent it is covering, so that is your target. Means whenever normally we could also pick a position, means normally whenever we are taking a picture of any object, we will target at particular point on that object, then so that I can set my camera on that particular line. Then from that point I will decide how much right side I want, then how much left side I want, how much bottom, how much top. If I am not able to cover my intended area, then again I will move that camera. Like that means I am aiming at particular point in those objects so that I can cover my interested area. That is what the meaning of second point. Then we must decide on the camera orientation. Then afterwards we must decide on the camera orientation. Means somebody might take your camera horizontally, somebody may rotate camera vertically, again somebody like this. That is orientation. How much orientation you want to do for taking that picture, that we have to decide. Then finally, when we snap the shutter, the scene is cropped on the size of a selected clipping window, and light from the visible surface is projected on the camera film. Then afterwards, then whatever area your camera has covered, only that part of the camera, that part of the image has to be taken into projection plane. That is what clipping means. Whichever is not covered in your camera lens, in front of your camera lens, normally that part is clipping. Means that part we are cutting out. Then only whichever objects are comes through my lens, only those part we will capture and we will print on that. That is what clipping, right? Means you crop the size of the selected clipping window, and the light from the visible surface is projected on the camera film. This is the procedure normally we will follow. Then some of the viewing operations for a 3-dimensional scene are the same as or similar to those used in the 2-dimensional viewing operations. Again here, some of the viewing operations for the 3-dimensional scene are the same as or similar to those of 2-dimensional viewing. Again, there is some similarity between 2-dimensional viewing and 3-dimensional viewing pipeline, right? In 3-dimensional viewing, however, the clipping window is positioned on selected view plane. Again, in 3-dimensional viewing, however, the clipping window is positioned on the selected view plane, and scenes are clipped against the enclosing volume of a space which is defined by the set of clipping planes. Right? In 2-dimension, what we are doing, clipping window is a rectangle only which has only two sides. In a 2-dimensional clipping, only clipping window has only two, means only it has x and y. X and y means it is a rectangle. It is a simple rectangle or simple square. In that, whatever object is there, only that part we are taking in 2-dimensional. But in 3-dimensional, it is not the case. In 3-dimensional, we have to take x and y. We have to consider x and y. At the same time, we have to consider z also. That is depth information we have to add. That's why here clipping window, normally we will not call this as a clipping window. Here we will call clipping volume. That is clipping volume means the clipping window is nothing but it has consist of set of clipping planes. Means that is one cube. Clipping window in this case is a cube, right? In that cube, whatever objects are there, that object we have to capture, then that object we have to project, that object we have to display. That is what the meaning of this. In the three-dimensional viewing, however, the clipping window is positioned on a selected view. Here also we have to place clipping window on selected view plane, and scenes are clipped against the enclosing volume of a space. Means we have to clip that objects, how much I want right side, how much I want left side, how much front, how much back side, how much top, how much bottom. This is volume. In this volume, whatever objects are there, those objects we have to display it in our monitor or our film. But it was not the case in two dimension. Only two dimension we have taken the rectangle, then whatever objects is there, right, this within this, whatever object is there within this, whatever object from top bottom, those objects we are taken. We are not taken front and back in two dimension, but in this case we have to take front and back in two dimension. That's why it is a clipping volume, right? That is clipping plane. Means clipping volume is combination of clipping planes. There are this plane, this face, front face, back face, top face, and bottom face. This is the clipping planes, right? The viewing position, view plane, the viewing position, view plane, clipping window, and clipping planes are all specified with the viewing coordinate reference frame, right? The viewing position, view plane, clipping window, and clipping planes are all specified with the viewing coordinate reference frame. Means from where you want to take that object, with a reference to that you have to place these all, specify all those points, right? The viewing position, view plane, clipping window, and clipping planes are all specified with the viewing coordinate reference frame, right? Then next, then 3D viewing pipeline. How that 3D viewing pipeline works, right? The general processing steps for modeling and converting a word coordinate description of a scene to a device code. Means here intentionally what we are doing in 3D viewing pipeline, the objects are, as we are told, in word coordinate. Then object, word coordinate object, somehow we have to convert, somehow we have to process, all processing we have to do. Then at the end we have to display it in device coordinates, right? As I told, in word coordinate object is in 3D word, but device coordinate has 2D. Then in this process, somehow we have to set the reference point, then clipping, then projection, right? Then convert 3D to 2D, then it display it in device. This process has to be done in 3D viewing pipeline, but this is done by stage, right? That is what 3D viewing pipeline, right? Then first is, as I have told, basically objects are in model coordinate. Means every object individually will draw with respect to their origins. We will not consider as common origin for drawing those objects. I'll draw one object. During class I have taken a cycle. When you want to draw a cycle, I'll draw front wheel first, then I'll draw second wheel first, then I'll draw handle. All those things separately, they have their own origins. With respect to their origin we will draw. Then modeling transformation, we apply the modeling transformation. Then after applying the modeling transformation, then they will come to world coordinate. Means they will come with their own, afterwards they will start referring only one origin. With respect to that origin, those all objects has to be aligned, right? This is what happens, right? We will see one by one. 3D viewing pipeline, right? As I have told, construct this shape of individual object in a scene with modeling coordinates. As I have told, separately you construct front wheel, back wheel, seat, handle, all those things separately we will construct. Then to that we will apply the modeling transformation. We will apply the modeling transformation. After applying modeling transformations, and place the objects into appropriate positions with the scene, that is world coordinate. Then afterwards you take all objects in a particular scene, then with only one origin align all objects with respect to only one origin, right? One reference point. Then whichever with respect to x, y, you will align all those objects. That is called world coordinate. Then afterwards, then we'll move to viewing transformation, right? 3D viewing pipeline, viewing transformation. Word coordinate positions are converted to viewing coordinates now. Now world coordinate positions are converted to viewing coordinates. The viewing coordinate system defines the viewing parameters. The viewing coordinate system defines the viewing parameters, including the position and orientation of the projection plane. Means it will define camera position, from where you want to take the picture, then includes the position and orientation of the projection plane. Then how to orient that camera, orientation has to be defined here, which we can think of as a camera film plane, right? Means in this viewing transformation, nothing but we are setting the camera positions, right? Camera position we are setting. Then where you want to take that projection, where you want to take that picture image, that we have to decide here. then what orientation you want to do with your camera, everything has to, all parameters have to set in viewing transformation. Then after viewing transformation, then those points will be in viewing coordinates. Now those will be converted into viewing coordinates. Then afterwards, then convert the viewing coordinate description of the scene to coordinate position on the projection plane. Till that time all the points are in 3D. Till this stage all the points are in 3D. Then convert the viewing coordinate description of the scene to coordinate positions on the projection plane. A two-dimensional clipping window corresponding to a selected camera lens is defined on the projection plane, and the three-dimensional clipping region is established. This clipping region is called clip view value, right? In this case, we have two-dimensional clipping window corresponding to the selected camera lens, means whatever camera, wherever you have focused that camera on particular object, then that region you identify, that is a two-dimensional clipping region. That is a two-dimensional clipping region corresponding to your scene. This is defined on the projection plane, that is defined on the projection plane, and the three-dimensional clipping region is established. With respect to that, you establish a three-dimensional clipping region. By using two-dimensional only can set left, right, top, bottom, but since it is a 3D object, you have to take how much from which front side you want to till how much back side you want to see. That is what clipping volume you have to create. This clipping region is called the view volume, right? That, as I told, this clipping volume will be in like a cube, means in a particular cube whatever objects are there, that object you want to display. That is what we have to do here. After this, the objects are in, after this the object coordinates are in 2D. After projection, the 3D object will be converted to 2D object. Till the projection transformation, the objects are in 3D word coordinate, right? After this, it will come in a 2D coordinates. Then afterwards, you will convert projection coordinates, right? Then afterwards, position. After that, then position on the projection plane will then map it to the normalized coordinate and output device. Then afterwards, all those has to map it to the normalized coordinate and output device. All parts of the scene outside the view volume are clipped off. Then in this case, normalized transformation and clipping, all the parts which are outside your viewing volume, those has to be clipped, right? Means whatever are there in cube, only take those objects whichever are outside your cube, then clip out, right? That will be done in normalization and transformation. Then as a two-dimensional viewing, the viewport limits could be given on normalized coordinate or in a device coordinates, right? Then afterwards, you can limit that to normalized coordinate or device coordinate, convert to normally we will keep all the coordinates in normalized coordinate. Then afterwards, whenever we are displaying from that normalized coordinate, then depending on device coordinate, we will map those the normalized coordinate to device coordinate. Then we will start displaying on our device coordinate, right? Then next is 3D viewing coordinate parameters. Then how to do this? All those things, how to do this, right? 3D viewing coordinate parameters. Establishing a three-dimensional viewing reference frame is similar to setting up the two-dimensional viewing reference frame. As I told, establishing a three-dimensional viewing reference frame is similar to setting up the two-dimensional viewing reference frame. We first select a world coordinate position P0. First we will select a world coordinate position P0, X0, Y0, Z0 for the viewing region. Means we have to set, as I told, we have to set first camera position in world coordinate, right? Which is called the viewpoint, or viewing position. Sometimes the viewpoint is also referred as the eye position or the camera position. As I told, means P0 is nothing but, if you analyze this one with your real world camera, then this is a camera position we have to set in world coordinate. That is P0. Means from which place you want to take the image. Right? That's a P0 you have to set. That is called viewpoint or viewing position. In some time that is called eye position or camera position. Then and Y specify view up vector V, which defines the view Y view direction. Means view up vector means orientation of our camera. View up vector V will tell what orientation you have made with that camera. Whether you have tilted that camera, whether you have kept that camera parallelly, whether you have kept that parallel vertically. That orientation of camera will be set by setting the view up vector, that is a V, right? That is Y view direction. That is called Y view direction. Then we also need to assign a direction for one of the remaining two coordinate axes. This is typically accomplished with the second vector that defines the Z view axis with the viewing direction along this axis. Means already we have set Y view direction by setting the view up vector, that is V. Then along with this, one more direction we have to set, that coordinate axis we have that is Z view, right? Z view axis, which is the viewing direction along the axis, right? Z view means along that, normally along Z axis we are viewing the object. By default, whenever we are taking an image, whenever we are taking capturing a picture from any camera, we are by default we are viewing along the z axis, right? Along the z axis. Again, depending on what type of right hand and left hand coordinate system you used, that depends. If you are using right hand coordinate system, you are viewing along negative z, right? Because in right hand coordinate system, positive z is towards you. You are viewing from this direction, nothing but you are viewing in negative z direction. By default, whenever you are taking any picture, we are viewing in z along with the z direction, but whether you are viewing positive z or negative z, that depends on which coordinate system you have taken. If you have taken right hand coordinate system, then you are viewing along negative z, right? This is what I have to say. We have to set that is the z view, right? Then specifying the viewing coordinate system. Now we have to specify one by one for taking image. Means we have to go step by step, right? First you have to as I told, first you have to set viewpoint, means camera position. First, in real life we will do normally. In real life also we are doing. First we will set the camera. How to set camera? In real life we have a hardware camera, then we will go and place that camera here. But here we don't have a camera. Everything is imaginary. Means everything we have to set mathematically. That's why we have to set that one, camera position or viewpoint, right? We first pick a word coordinate position called viewpoint. That is origin of our viewing coordinate system. That is origin of our viewing coordinate system. That is a P0 is a point where a camera is located. In this image you can see that is a P0 is a camera. P0 is a camera position. It has the x coordinates x0, y coordinate y0, z coordinate z0, right? Then that is the z axis, z view, x view, y view, right? This is world coordinate, zw, xw, yw is the word coordinate. In this word coordinate, I means in a 3D word, I am setting some camera in some place. I am setting some camera in some place. I have set my camera at P0. Means my camera is at P0. Again, it has its reference point. It is not true. It may not be true that always my camera reference and world coordinate reference may be same, right? Because I may stand anywhere, then my camera may orient anyway. That's why the xw, yw, zw may not be same as yv, xv, zv, right? That is what P0 we have set in 3D word, right? Then afterwards we have to set the view plane normal vector. Then we have to set the view plane normal vector. Then where you want to take that image, means film, your camera film, where you want to take that image, that is a camera film, right? Nothing but camera film, that view plane normal vector. Then because the viewing direction is usually along the z view, as I told, because we are using viewing in z direction, z view axis. The view plane, also called the projection plane, that view plane or also called the projection plane, is normally assumed to be perpendicular to this axis. Means if you are viewing in this direction, then where you want that picture, definitely you want that picture somewhere here. Means nothing but you are viewing like this, that picture you want somewhere here. This is what normal. This is projection plane. This is a projection plane, right? On this projection plane you want the image. How you are viewing? You are viewing like this. You are viewing that side. That object image you want here. That is viewing projection. This is called projection plane or view plane, right? Is normally assumed to be perpendicular to this axis. Means normally it is perpendicular to your z view axis. This is z view axis. You are viewing in this direction. Normally it is perpendicular to your z view axis. That's why this is projection plane. Then next we select the positive direction for the viewing z view axis by specifying the view plane normal vector n. Next we will select the positive direction for the viewing z view axis by specifying the view plane normal vector. Means you specify view plane normal vector. Normal vectors will be always exactly perpendicular to that plane, right? Normal vectors are always perpendicular to those plane, whichever plane you are taking, right? The direction of n is from the look at point L to the view plane. Means direction of n is from the look at point L to the view plane, right? We will see that again next also it will come, right? This is the image. Means if you want to see this one L, means you are targeting for particular L, then that normal is coming from that side. It is coming towards your view plane. It is coming towards your, means this is a look at point, means you are looking somewhere on that object, that is L. Then from that your normal is coming, it is towards your view plane, that is exactly perpendicular to your view plane. It is like this, means your view direction is like this, then that normal is coming towards like this, that is exactly perpendicular to your view plane, right? Then in addition, an additional scalar parameter is used to set the position of the view plane at some coordinate value zvp along the zv axis, right? Then an additional scalar parameter is used to set the position of the view plane at the some coordinate value zvp along the z view axis. This is additional advantage we have in computer graphics. Means this is not there in real life cameras. Means you cannot change the view plane position. Always view plane position in your camera is always backside your camera. Always backside your camera, right? Or at exactly at origin. It may be exactly at origin. But that additional flexibility we have in OpenGL, you can move that view plane in the z-axis anywhere, wherever you want. In that z-axis, you can move the view plane. Means where you want to take image, that image plane can be changed along the z-axis. That can be there in this. That's why this, if you can see here, zvp is greater than 0, then that view plane is towards positive z. That view plane is positive z. If zvp is exactly 0, then that view plane is at exact origin. If that zvp is less than 0, then definitely that view plane is towards negative z. That can be made, means you can move your projection plane along the z direction, but it is not possible in real life camera. This is there in OpenGL, right? The view plane is always parallel to the, that's why the view plane is always parallel to the x view and y view. If you see that view plane is always parallel to the x view and y view plane, right? If you see from this image, always that view plane is always parallel to the, if it is x, this is y, then view plane is always parallel to this. If it is x, if it is y, then view plane is always parallel to this x view and y view, right? Will display it on the output device. Then vector n can be specified in various ways. Again, that vector normal, surface normal, can be specified in various ways. The direction of n, direction for n is defined to be along the line from the word coordinate origin to selected point position. Then the direction of for n is defined to be along the line from the word coordinate origin to the selected point position. Means you can specify that surface normal, that is n from your p camera position to the object, towards the object. That also can be possible. Means that normal from your object to your camera, your object to your camera can be set. Otherwise, other system take n to be in the direction from the reference point p reference to the viewing origin p0. Other means the direction for n is defined to be along the line from the word coordinate origin to the selected point position, right? Word coordinate origin to the selected point position, or some reference point on your object to your point, right? Reference point to viewing origin, that is p1. That both way, means both direction you can set that normal. Either you can set from this plane to this, or from that object to this, right? That can be done. The reference point is often referred to as look at point within the scene, right? That reference point is nothing but look at point at the scene, right? This is how to set the camera, right? Then specifying the view coordinate system, view of direction. Now means we have set normal vector. Then we have to set the vector. We have set normal vector. We have set the z axis. Now we have to set the up direction. Up direction means orientation. You have to set orientation of a camera. In real life camera, if I tilt, then camera will be rotated. But in OpenGL, how to do this? In graphics, how to do that one? Everything is mathematical. Means if you set that view of direction, along with the y direction, then your camera is as it is. But if view of direction is slightly away from your y, then definitely you have tilted. Like that, everything is a mathematical. Everything, whatever concept, whatever practical will do with the camera, same has to be done with mathematically in OpenGL, right? Once we have chosen a view plane normal vector, after choosing view plane normal vector n, we can set the direction for the view of vector v. Then you have to set the direction. Normally view of vector is exactly vertical, that is vy. Y axis is view of vector, right? If it is y vector, y axis and view of vector exactly coincides, then you have kept camera normally. But if there is a change in view of vector and y, definitely you have tilted the camera. That is what we are setting here. This vector is used to establish the positive direction for the yv axis. Means we are setting the positive direction for the y. If y is exactly like this, then normally you hold the camera. But y is something like it is not exactly perpendicular, then definitely you have tilted that camera. That is that specification we are doing here. Then v is projected onto the plane that is perpendicular to the normal vector. V is projected onto the plane that is perpendicular to the normal vector, right? V is normally projected onto the plane that is perpendicular to normal vector. Normal vector is like this, v is like this, v will be projected here. normal vector is from this projection plane, then v will be like this, then v will be projected on this plane, right? That is what. Usually v is defined by selecting a position relative to the word coordinate origin. V is defined by selecting the position relative to the word coordinate origin, so that the direction of the UOP vector is from the word origin to this selected position, right? Then in general it can be difficult to determine the direction for v that is precisely perpendicular to n. In general, in reality it is very difficult for calculate v exactly perpendicular to n, right? That's why what we will do, we can choose any direction for the UOP vector v so long as it is not parallel to n, right? It is not parallel to n means you cannot take UOP vector and normal parallel, right? Always UOP vector must be perpendicular to n, v must be perpendicular to n, right? A convenient choice is often in a direction parallel to the word yw axis. That is, we could set v equal to 0, 1, 1. Means if we set v of vector v equal to 0, 1, 1, 1, then nothing but v is exactly aligned with your y-axis. V is exactly aligned with your y-axis. Like that you can set the v of direction, right? This is what here. First, if it is not aligned, means you are not decided exactly at that, then how to take how much, how it is there, that you project it in a projection plane, you project that input, actually input v have given like this, but it is not exactly perpendicular, it is not exactly like this, then you project it in plane, then you adjust v, right? That automatically n and v will be perpendicular, automatically perpendicular, right? This is what desired up direction. In right side you can see desired up direction, actually v is this, if desired up direction, then you take a projection, then you can adjust that one, right? Then here now we have set v, that is y-axis, v is nothing but y, right? U of vector is nothing but y-axis. Then we know that n is nothing but z, view, n surface normal is nothing but z view, means we know two axes here, that is we know y, we know z, still we don't know what is x, right? We want all three axes to be known, then only you can decide whether you are using right hand system or left hand system. As I told, this is right hand system, this is left hand system. Means in right hand, left hand, what is the difference? In right hand system, z is positive towards the viewer, in left hand system z is positive away from the viewer, means z is negative towards viewer, that we have shown. But how to derive this one in OpenGL, how to derive this one in software, means whether we are using right hand system, whether we are using left hand system, that we have to derive here. Depending on right hand system, left hand, right hand system, viewing will change, right? If you are viewing in z direction, then if you are viewing in positive right hand system, as and when you move, your camera moves, means you start increasing distance. When you start increasing distance of your camera, nothing but when you take away from that origin, when you are taking away your camera, you are taking away from origin, definitely you are increasing, the depth is decreasing, means positive is this side, you are going this side, that is means the object is going towards negative side. But at the same time, if you are using left hand system, whenever you are taking, that is a plus and minus will change. That's why we have to derive that whether you want to use right hand system or left hand system, that has to derive by using this. That's why left handed viewing coordinates are sometimes used in graphics packages with the viewing direction in the positive z view direction. That's as I told, viewing direction is positive z. If you are using left hand system, means you are viewing in positive z direction, if you are using left hand system. But right hand viewing systems are more common because they have the same orientation as the word reference frame. In this case, we are viewing negative z direction. In right hand coordinate system, we are viewing in negative z direction. In left hand coordinate system, we are viewing in positive z view direction. That's why we have to decide which you are using. That's why we want all x, y, z, right? But till now we know only y, we know z, we don't know x. We have to calculate x here, right? Then because the view plane normal defines the direction for the z view, as I know, if you set the n, it will give the z view, z axis, it will give the z axis, and the view of vector v is used to obtain the direction for the y view, right? Means when you set n, nothing but you are setting z. When you are setting v, nothing but you are setting y view. We are setting y axis. We need only determine the direction for the x axis. Now still, but we are not set any value for the x. Only a set normal surface normal we have set, that is a projection normal, projection plane normal we have set, then view of vector we have set. Nothing but we have set till now, we have set only z and y. We don't know what is the value of x. That's why we have to calculate that x, right? Then using the input values for n and v, then how to calculate x, right? Using the input values for n and v, we can compute the third vector u. We can compute the third vector u, that is perpendicular to both n and v. That is perpendicular to both n and, means always the x is perpendicular 90 degree with ay, it is 90 degree with z. That is perpendicular to both n and y, right? Vector u then defines the direction for the positive x u axis. Then vector u defines the direction for the positive x axis, positive x u axis, right? We determine the correct direction for u. We determine the correct direction for u by taking the vector cross products of u and n so as to form a right hand viewing frame, right? We can determine the correct direction for u. Again, you have to calculate the correct direction. You cannot calculate negative x, you have to calculate positive x, right? That's why correct direction for u by taking the vector cross products of u and n so as to form the right hand viewing frame, right? But after that you automatically will get right hand viewing frame, right? The vector cross product of n and u also produces the adjusted value for u, means if v is not exactly perpendicular, if you adjusted that v, right, that can be set by taking the n and u, vector cross product n and u also produce the adjusted value for v perpendicular to both n and u, right? Both n and u along the positive y view axis, right? This is how we have to set the, we have to decide x, y, z. That is by deciding that, then we can calculate what is the right hand, right? Where the right hand system will come, right? Then following these procedures, we obtain the following set of unit axis vectors for right hand viewing coordinates. Now then, after knowing these values n, v, u, after calculating n, v, u, then you can calculate the right hand coordinates. That is n equal to n by absolute n, that is you will give nx, ny, nz, right? Then positive n direction, that will give the positive n. Then u, that is v into n, then v into n, that is what, ux, uy, then that is positive u, then v equal to n into u, that will give the positive x, right? This is the right hand coordinate system. Like this we have to calculate right hand coordinate system. This is how we have to set the parameters for 3D objects, right? Then generating a three-dimensional viewing effects. Generating three-dimensional viewing effects. By varying the viewing parameters, we can obtain different views of objects in a scene. By varying the viewing parameters, we can obtain different views of object in a scene. Means how to generate three-dimensional viewing effects, right? For instance, from a fixed viewing position, we could change the direction of n to display objects at positions around the viewing coordinate system, right? For example, one object you have taken here, then that surface normal is from this, right? You take one image, then take the surface normal, change the surface normal, automatically it goes back side, then set the surface normal side, set the surface normal side. Means just by changing surface normal, you can nothing but you are capturing the objects of other faces. You are capturing the other objects of other faces. That is what first step, right? In interactive application, the normal vector n is the viewing parameter that is most often changed. In the interactive application, the normal vector n is the viewing parameter that is most often changed. Means nothing but here in real life, whenever you are taking an image of tree, what you will do? Means whenever you are taking don't go for image of tree. If you want to take an image of one cup, tea cup, at that time you will fix a camera here somewhere like this. You will fix a camera. They will take first picture from one side. Then you want to take other side image. Instead of moving your camera, what you will do? Just you will rotate that cup. You will rotate that cap. Nothing but surface normal will be rotated. Then you will take a picture, right? Again you want other side. You rotate that. Means instead of moving camera, you rotate objects. That is what the meaning of this, right? In interactive application, the normal vector n is the viewing parameter that is most often changed, right? Then that is one way of taking different faces of objects, right? 3D means by combining this you can give the 3D effects, right? Then if you want to simulate an animation panning effect, as when the camera moves through a scene or follows an object that is moving through a scene, we can keep the direction for n fixed as we move the viewpoint, right? In this case, what we are doing, for example, you are taking a picture of tree. At that time you cannot rotate the tree. At that time you cannot rotate the tree. In this case, you keep the surface normal as it is, you move along the tree, you move around the tree, means nothing but camera is moving, right? Like this can be also done. That is the meaning of this. If we want to simulate an animation panning effect, as when the camera moves through a scene or follows an object that is moving through a scene, we can keep the direction for n fixed. You can keep the direction for n fixed as you move the viewpoint. You move around the tree. You take a camera, then you move around, nothing but you are capturing in a 3D. Then again combine this, then you display, right? Like this here. First, viewing an object from a different directions using a fixed reference point. Reference point is fixed. Reference point is fixed. Just you have rotated that cup like how you want, right? First you have taken first image from this side, right? Then you have rotated. Then from that side, then you have rotated. Like this, surface normal is changing. Surface normal is changing in first case. In second case, surface normal is fixed. You are changing. You are moving. You are moving, panning across a scene by changing the view position. Means view position you are changing. View position, first time you have viewed from this side, next time you will go there, view position you are changing. In first case you are changing surface normal. You are changing surface normal. In second case, you are moving the camera, means viewing position only you are changing, right? You are moving around the object, right? This is what the 3D effect, right? This is regarding 3D viewing, right? Again next part, again projections and how to still we are not transferred, means this is still it is in real world. Then to do this, to take an image, again we have to do some transformation, right? Then what is the projection, all those things concept we will discuss in next topic, right? By this today we will end introduction about 3D viewing, how to set the parameters, right? How to set view up vector, how to set surface normal, how to calculate a x-axis, so that I can decide what is the right hand coordinate system, that we have discussed in today's lecture. This is what the 3D viewing. Thank you.